Now we continue to learn chapter 3, vector spaces, and now we learn about section 5, change of basis. Many applied problems can be simplified by changing from one basis to another, and changing from one coordinate system to another, we do this transform, y equals s times x, where y is a new coordinate, and x is the original coordinate, and s is a non-singular matrix. So we do the coordinate transformation. So see this figure, it's like in this coordinate system, the points is like in this position, and if we adjust the coordinate system like here, this means we use a new basis. The points now becomes like here. So they are essentially the same, however, maybe much easier to see from this figure. Okay. Now we consider to change coordinate in R2. The standard basis for R2 is E1, E2, right? We have this two standard basis. This standard basis, and any vector x in R2 can be written as x equals x1 times E1 plus x2 times E2. Here, the scalars x1, x2 are the coordinate of x with respect to the standard basis. Okay, and any other basis for R2 we write as a vector y, vector z. They constitute another basis, and any vector x in two-dimensional real vector space can also be expressed as a linear combination of these given two vectors. So x can be written as alpha times y plus beta times z. The scalars alpha and beta are called the coordinate of x with respect to the ordered basis y, z. For example, okay, y here is this vector 2, 1, and this vector 1, 4. They are linearly independent. So we have y here, and we have z here, and x equals 7, 7 can be written as a linear combination. This is z vector. X vector can be written as a linear combination of y and z, which equals 3 times y plus z. Okay, and then we know that 3, 1 is the coordinate of this vector x with respect to this coordinate system y and z. If we consider the standard basis, then its coordinate should be 7, 7. However, now we consider new basis. The basis is consists of y and z. Then its coordinates is just the scalars before this vector. So the new coordinates is 3, 1 of this vector x. Okay. Now we see an application to make it clear why sometimes we want to use other basis, not the standard basis. Okay. Here, a population migration, which said that 30% of people lives in the city and 70% lives in the suburbs now. And we know that in each year, 6% of the people living in the city will move to the suburbs. Okay, and also 2% of the people living in the suburb will move to the city. We have this migration, population migration. And the problem is ask you after n years, what is the percentage of people living in the city and the suburbs? So this one can be computed by this equation, this xn equals a power n times x0, where a is this matrix. Because for now, 0.3 lives in the city, right? And 0.7 lives in the suburb. And we know that we do the matrix multiplication. We want the first component still be the people living in the city. Okay, so For the people living in the city, we know 0.94 will be still in the city. So here we use 0.94 here. And here, because this number will times 0.7, so this number should be the percent of people which before living in the suburbs now move to the city. So here is 0.02. Okay, and in order, this second component represents the percentage of people living in the suburb. So here we know 0.06 before in the city now moves to the suburb. Okay, and still 0.98 still lives in the suburb. Before suburb, now still suburb. Okay, so we do this multiplication. We can get next year how many people live in the how many percentage of people live in the city and live in the suburb from this vector. Okay, and if we do power n, we will get after n years how many what is the percentage of people living in the city and what is the percentage of people living in the suburb. Okay, so how to compute this? Especially how to when n tends to infinity, what the percentage. Okay, we can do like this. Let us choose new basis vectors u1 here, u2 here, and we can check that for this special two basis vectors, we have a times uj equals lambda j times uj. Okay, you can check in fact a times u1 just equals 1 times u1, so lambda 1 equals 1, and you can also specify what is lambda 2 for u2. So this like if a function on this vector, basis vector, just a new vector, this is just a new vector which is in the same line of uj. Okay, and because we know xn equals a power n times x0 and x0, now we can express it as a linear combination of these two basis vectors. It is just 0.25 u1 minus 0.05 times u2. And for this multiplication, we can have two terms. It's an power 0.25 u1 minus an times 0.05 u2. And for the first term, it equals 0.25 times a power n u1. Because a u1 equals u1, so a power 2 u1 also equals a times u1 equals u1. So a power n u1 also equals u1. So the first term just equals 0.25 times u1. And the second term, you see here is 0.05 times 0.92 power n u2. Here lambda 2 is 0.92. So this is smaller than 1. Its power n when n tends to infinity should be 0. So eventually when n tends to infinity, xn just equals 0.25 u1. So 0.25 u1 is just this one. See? So we can have the steady state of the population, the percentage of population living in the city and living in the suburb. Now we consider changing of coordinates. The standard basis for R2 is E1, E2. We know this. And we wish to use a different basis. Say we use U1 here, 3, 2, U2 here, 1, 1. The question is, given a vector x, the coordinates is x1, x2 in R2. If we just write x equals its coordinate as x1, x2, we use the standard basis to have its coordinates. Otherwise, we will say under which basis we can get this coordinates. Okay. Find its coordinates c equals c1, c2 with respect to the new basis vectors u1 and u2. So how to do this? We can draw this figure. Okay, here under the standard basis e1, e2, we have the coordinate vectors here x1, x2, and under the new basis vectors u1, u2, we have the coordinates. Here is C1, C2 with respect to U1, U2. Okay, and we know the x vector, they are same. It is the same vector no matter in the standard basis or in the new basis. Okay, so x can be written as E1, E2 times its coordinate vector x1, x2, which is also equals the new basis U1, U2 here times its corresponding coordinate vectors C1, C2 here, which equals U, the matrix U times C1, C2. So this means if I know the coordinates of x, this vector x, with respect to U1, U2, then I know the coordinate vector of x with respect to the standard basis very easily, because x can just equal the u times this coordinate vector C1, C2 and this new basis. So from other new basis to standard basis E1, E2, we can just write u here. So this means x1, x2 equals u times C1, C2 here. So u is a transition matrix from new basis to the original standard basis. And if we know the coordinates with respect to the standard basis, and we want to compute the basis with the new the coordinate vector with the new basis C1, C2, then you will have C1, C2 equals u inverse times x. So if this one is known, this x1, x2 is known, you want to know this one, this coordinates vector C1, C2. So its transition matrix is U inverse. You just use U inverse times this vector. Get it? From a new basis to the standard basis. This means this coordinate vector is known. Then you just use U as its transition matrix. On the other direction, if the coordinates of vector with respect to the standard basis is known, you want to know the coordinate vector with respect to the new basis, then the transition matrix is U inverse. Then C1, C2 equals U inverse times x1, x2. Okay, now we see an example. Let B1, B2 given and x here. So x here means they are the coordinates with respect to the standard basis, because we don't mention it's basis. Okay, find the transition matrix from E1, E2 to B1, B2 and determine the coordinates of x with respect to B1, B2. So here, the transition matrix should be from standard basis to the new basis. So the transition matrix is U inverse, remember? So U inverse should be B1, B2 inverse, okay? And then the coordinate of x with respect to B1, B2 should be U inverse, that is B1, B2 inverse times is x1, 2. Okay. Now we consider another problem. For example, in R2, we want to change from one basis, V1, V2, to another basis, U1, U2. How to do this? Before we consider from standard basis and the new basis. Now, all the two bases are general basis from V1, V2. Here is U1, U2. The idea behind this are the same. You just represent the same vector x. So x equals C1, V1 plus C2, V2 equals D1, U1 plus D2, U2. So C1, C2 is a coordinate vector with respect to V1, V2. And D1, D2 are the coordinate vector, is a coordinate vector with respect to this basis, U1, U2. Okay. And you write the matrix composed by V1, V2 as V. You write the matrix composed by the column vectors U1, U2 as U. And then you can write it as V times C equals U times D. Okay. Now you want to changing from basis V1, V2 to another basis U1, U2. This means C is given. C is known. Okay. So D is what you want to get. So D just equals U inverse times V times C. So you can also view this as a two-step process. Or you can also consider in this way. Now, we want to get from V to U, right? You can have an intermediate here, an intermediate step. Okay, you first transform from V to E, and then from the standard basis E to U. You know, from the V to E, as a transition matrix is just V, right? Because you from arbitrary other basis to a standard basis is transition matrix, just this matrix itself. And then from this standard basis, E1, E2, you want to transform to a coordinate system with respect to U1, U2. And this is from standard basis to other new basis. So its transition matrix should be U inverse, U inverse. So now from V1, V2 to U1, U2, you should first do transmission from here V1, V2 to E1, E2. So here is V first, and then you have U inverse. Okay. Now we see an example. Ask you to find the transition matrix corresponding to the change of basis from V to U, where V1, V2 given, U1, U2 given. So the first way, I think, which is easier to remember, easier to understand, is that you just write the coordinate system, the coordinates vector with respect to V1, V2, for example, is like C1, C2, this column vector, and from U1, U2 is like D1, D2 is coordinate vector. Then you just write X can be written as this matrix times the column vector C1, C2 equals also this matrix times its coordinate vector D1, D2. And then because V1, V2 given, U1, U2 given, and from this basis to this one, so the coordinate vector with respect to this one is known. So you just compute how to compute this coordinate vector. Then the transition matrix is easy to see. Okay. And now you can also using this idea for general vector space. Okay. We first see the definition. Let V be a vector space and let E be composed by these n vectors V1, V2 till Vn. This is an ordered basis for V. In order to see the coordinate vector, we emphasize you should consider the order of the vectors appear. Okay, if V is any element in V, then the small v, this vector, can be written as V equals C1V1 plus C2V2 plus till plus CnVn, where C1 till Cn, they are scalars. We can associate with each vector V a unit vector C here, composed by the scalars before this given ordered vectors and vectors. The vector C defined in this way, we just call it the coordinate vector of V with respect to the ordered basis E, where E is given here. Okay, in this order, and we denote the coordinate vector in this way. Here is V and subscript E here. The CIs are called the coordinates of V relative to E. Okay. Now we see this example. Here we consider in R3, we have this basis E here and this basis F here, composed of 3 different vectors. Okay. Ask you to find the transition matrix from E to F. So this one is also, you can use this equation. You can write any vector X which equals E times its coordinate vector equals F times its coordinate vector, and you determine from which matrix, which basis to which basis. From E, then the coordinates with respect to this one is known. You just express the coordinate vector equals a matrix times its coordinate vector with respect to E, and this matrix is just the transition matrix. Okay. And now, if X given you, Y given you as an expression, linear combination of vectors in E, so they are the coordinate vectors with respect to E. Okay. ask you to find the corresponding coordinates of x and y with respect to ordered basis F. The transition matrix is known already, so its coordinates just equal this transition matrix times its coordinate vector. For x, its coordinate vector with respect to E is 3, 2, minus 1 in this order, and for y, the coordinate vector with respect to also E is 1, minus 3, 2 in this order. Okay, now we further address transition matrix. We know that the transition matrix must be non-singular matrix. So if V is any n-dimensional vector space, it is possible to change from one basis to another by means of an n by n transition matrix. A transition matrix is necessarily non-singular, must be non-singular. Any non-singular matrix can also be regarded as a transition matrix. So here is E, one basis, right? And F here another basis. And you can write WG as a matrix S. You do this summation I varies from 1 to n as ij with I equals 1 to n. And S will be the transition matrix corresponding to the change of basis from E to F. Okay. And in many applications, it's important to use the right type of basis for the particular application, as for the population migration we mentioned before. Sometimes we like to use orthonormal basis to solve least squares problems, for example. So in chapter 5, we will consider about orthonormal basis. And also, sometimes we like the basis consisting of eigenvectors of a matrix A. That's what we use in the previous migration, that population migration example. And we use, in fact, eigenvectors of this matrix to form the basis. So this considers about problems about eigenvalues and eigenvectors, and we will learn in chapter 6.